come to the place where Pangea, one of the many places where Pangea started to break up. About 200 million years ago, the supercontinent called Pangea started getting stretched out because it was heating up the Earth's mantle below it, because of blanketing so much of the Earth that the heat couldn't escape into outer space. And so it expanded and started stretching, and all over North America, the east coast of North America, the north coast of Africa, parts of Brazil, there are these cracks, and this is one of them. All these cracks trying to form the Atlantic Ocean. Magma exploited the crack, the weak spot in the crust, and came up and erupted out onto the surface. In some place in volcanoes, here in simply the form of a fissure flow, where it came out of a crack and just flowed across the land. Up high, some of the earlier basalt, the earliest lava flows show up, and those came up underwater and formed pillow basalt formations, just like you saw in the movie A Ring of Fire, talking about the lava flows under the water near Hawaii. Same kind of formation. You'll see these bulby shapes with sort of crusts around them. Other places you'll see it look like a sponge with lots and lots of bubbles. And those are the vesicular basalts that has vesicles, which are like little tiny vessels. Sometimes you'll see crystals that have formed inside them. As you get closer down here where I am pointing, if you look closely, you'll find some polished surfaces. These were not polished by glaciers. These were actually polished by rocks sliding past each other in an earthquake. We call that a slickenside. It's a Scandinavian word, which basically means rock that's been polished by an earthquake. Sometimes it's so polished that it turns into glass. At some point, the lava flows stopped, and it allowed the area to cool off enough that lakes started forming in the deep valley of the Connecticut Rift, and sandstone started forming down here, and it's panned across thousands and thousands and thousands of layers of sandstone moving up and moving forward in time as Mr. Lee turns the camera up towards the spillway of the dam. Up there, often are found fish fossils. All these layers of sandstone and the basalt are all part of that map on pages 21 and 22 of your fieldwork journal. And in fact, if you use your fieldwork journal map really well, you may be able to find lake bed 0, 1, 2, 3, 4, 5. You may be able to find the layers that happen to have lots of fish fossils or fish scales or even dinosaur footprints. I have found dinosaur footprints out here. People have found up near the dam up there, they have found fish fossils. Some fish fossils that were actually split by an earthquake fault were found there. Now, you may notice that I'm not standing straight up according to this camera view, and that is because all of the sandstone is tilted. Off to our east, that way, is the Eastern Border Fault, which is the boundary of the Connecticut Rift Valley. As Pangea was being pulled apart, the eastern half of this, after all of this was laid down, the lava flows happened, after all the sandstone was laid down, it kept stretching out a little bit more, and the eastern part of the whole valley dropped to about this angle. And so later on, after all of this tectonic activity had stopped for this region, this whole area got buried in sediment. Now where is all that sediment? The sediment, which of course came from the old mountains that used to be over here taller than the Himalayas. Those mountains are gone and have all been washed down to sea, but some of it stayed here in the form of the sandstone. So we've got recycled mountains that we're standing on right here that happen to have then later been tilted. Now, that got buried by sediment, and sometime in the last 20 to 50 million years, there was an uplift. Probably the crust underneath this area got hotter, and it lifted up because it was lighter as that heat expanded. So it lifted up, and then the river, which at that time, before that uplift, was actually pretty close to sea level, was no longer close to sea level. Now it was lifted up and started cutting its way down. So the whole Connecticut River Valley got re-eroded again, and all of this old Jurassic sandstone and Triassic basalt got exposed again for us to examine. Now, if we pan around to the river now, I'm not sure which way Mr. Wheat's going to go, but that's the way we're going. Okay, good. So we're panning downstream, and if you look across the river, following the line of the basalt ridge, you will probably notice that there's no basalt ridge on the other side. Why the heck is that? Well, that's because there's a fault line running down the river. The river actually follows a fault line, which is very common. Rivers will follow fault lines because they're the weak spot in the rock and things erode down through there. The fault shifts the basalt to the west over here. And so the lava flow goes out, it gets cut by the earthquake fault and moved over there. And so this sandstone that I'm standing on shifts over there as well. So if you're on the south side of the river, the layers that you're experiencing over there match up with layers further east on this side of the river. So what we've got right here are pillow basalt formations. These rounded areas, and this one in particular is really distinct. It has a sort of onion peel shape, layers of an onion that form when lava flows underwater and the outer crust cools really fast, and then suddenly it gets pushed out again by the molten lava inside that cooled crust of rock. And this is what we saw when we were watching Ring of Fire. The lava flows underwater in Hawaii, the newest land on Earth.